Welcome to my talk. This is going to be a talk on memory forensics. We're going to look at attacker techniques in malware that are considered somewhere in the moderate to maybe the advanced range, and we're going to be using memory forensics to detect that activity. For people who don't know me, my name is Andrew Case. I'm one of the core developers of Volatility. I'm also one of the developers of Registry Decoder for people who have used that. Published my first book recently, The Art of Memory Forensics. This was with the other Volatility developers. It was about 900 pages, looking at memory forensics across Windows, Mac, and Linux. Before I got into forensics, I spent a lot of time on this, kind of in the security world. I did a lot of reversing for vulnerability assessments. We did a lot of source code audits. I spent a lot of time doing penetration testing. Since then, I've mostly been in the incident response and the malware analysis world. So many people have used memory forensics before, besides the people at this first table, who I'm well aware of. Has anyone used it? Okay, so a few people. All right, so what we're talking about memory forensics, what we're doing is looking at RAM of the system. If you think of traditional forensics, if you go back to the mid-90s, they're looking at disk. So originally, forensics looked at disk images, looked at files on disk, network forensics as well, and then you start to get to memory forensics, which is where, as you're going to see, there's a lot of information that isn't contained in those other sources. The other thing to realize is that memory forensics often complements disk and network forensics. How many people were in this room for the last talk from David? Few people? Okay, we're going to see a lot of the things that he talked about. The talks kind of complement each other. He wants to be able to detect things, be able to fingerprint how attackers work, and memory forensics is one of the good ways we can do that. So what can be recovered when we're doing memory forensics? If you look at the first three bullets here, these are things that, how many people do live IR on systems? So you want to investigate it, you start running like system kernels or similar tools. How many people do that? A few? Okay, so these first couple bullets are things that those tools can certainly give you. The Microsoft API or whatever operating system you're dealing with, they can tell you the running processes, they can tell you modules loaded into the process, some information on network connections, where kernel drivers are loaded. We're going to see that doing that from a live IR perspective often can be futile because malware can very easily lie to those tools. And then if you look towards the bottom of the slide, these are things that there's no API for. So we're going to see you can recover console input and output from command.exe, from PowerShell. There's no API in Windows that you can pull that out of memory directly. We'll also see there's a number of artifacts that malware creates. Some of this is directly created, some of it's indirectly created by the APIs, and we can use that as well. Another interesting thing with memory forensics is application information. So if you have people that are using SSL browsing, if they're not logging things back to disk, your disk forensics is going to have anything if it's not written there in the first place. And when you look on the network, you might know, okay, well, the machine talked to this IP address, it used this port, but you don't know what the actual contents were. When we do memory forensics, though, we can kind of get an advantage there. If we look in memory, we'll see the plain text information that was sent on the network, that was typed into the browser, that was typed into chats, or we can just recover the encryption material directly, whether that's the key, whether that's the password, and then we can break that information open. So why is memory forensics so important? One thing to realize is that the view of the system you get is what is the full state of the system. So if you think of disk forensics or network forensics, you can certainly find a piece of malware, you can find an executable that ran, you can then reverse engineer it, you can do analysis on it, but it doesn't tell you the state of the actual infection. First is if you have memory on the machine, you know what exactly the application was doing, you know what the variables were, you know what data it was processing, so you know very specific information on a particular infection. And we'll see that later when we talk about some of the volatility plugins and when we talk about using Yarrow. Another thing for memory forensics is the ability to recover historical information. If you think of what the APIs do, it's all of the active data. It's what processes are running, what users are currently logged in, what pages in memory are actually still being used. But from a memory forensics perspective, we have access to all of RAM, whether the API exposes it or not. So when we go back to do our analysis, we can uncover information that might have happened a week ago or a month ago. So when you look at the strings, you'll see URLs, you can recover fragments of files, that again, there's no real way to get those off of a live system. We'll also see a couple slides of malware that operates only in memory. Again, if you go back in history a little bit, the attackers were winning for a while. They realized that the way people acquired machines, especially police officers and certain agencies, was you walk up to a machine, you pull the plug, you take the disk image back to your lab, and you do forensics. So what the attackers started doing was just only operating in memory. One of the first public examples from this was from one of the early precursors of Metasploit. So if you've ever seen Uninformed Journal, any of the hic.org research, they were the first people to start loading code and executables only into memory. And once that happens, if you pull the plug, all the evidence goes away. You can look on disk, nothing's going to be there, and again, only through memory forensics can we find it. And all of this is kind of summed up in what I have in red. It's that if you're doing memory forensics, you're necessarily going to miss information. A lot of the information isn't written back to disk. If it is written back to disk, it's in an encrypted form, and the same thing happens on the network. If you have even reasonably skilled attackers, everything that they push on the network is going to be encrypted. It's often going to have custom protocols, and unless you can reverse engineer that application to write a decoder, the network forensics isn't going to be as helpful to you as something like memory forensics is. Some documentation on memory forensics. We always have our book that came out, as I said. The Malware Analyst Cookbook is good as well. If you've never seen memory forensics, if you've never even looked at malware from a basic perspective, it's a really good resource. The other thing we have on the Volatility Wiki is the Community Documentation Project. So what we've done here is going all the way back to 2004, 2005, is we've indexed everything related to memory forensics, whether it was an academic paper, a thesis, a blog post, a conference presentation that went public. Really anything that we could find related to memory forensics is indexed on the site. And at this point we have around 250 items indexed. So if you want to see how people use memory forensics, how it evolved, that's a really good resource. So many people have used volatility before or seen it in use? A few people. Alright, so because I'm one of the volatility developers, because it's open source, this is what we're going to be using to do our analysis. For those who aren't familiar with volatility, it's implemented in Python. It's an open source project under GPL v2, and it's used to extract artifacts from memory. So this is going to automate a lot of the memory forensics analysis that we want to do. Some of the advantages that volatility has. So at this point, we have over 200 plugins in the latest release, and we also support a wide range of operating systems. So XP, Windows going back to XP, all the way through 2012 and 8.1. Linux going back to around 2005 through the latest releases, and then Mac Leopard 10.5 through the latest 10.9 releases. We have experimental support for 10.10 right now. We haven't really released it fully because it's still new, but we have support pretty much for any operating system you're going to see. We also have Android support, so you can get memory capture of your phone and then do analysis on that. The other reason people like volatility is because of what we hook into through Python. So we're going to see that volatility has automated ability to find hashes in memory, to do disassembly in memory, and we also have integration with Yarrow. How many people have used Yarrow before or seen it used? Okay. Has anyone used it in memory or only like on disk or other artifacts? A few people in memory? So before I could get into analysis, I wanted to spend a couple minutes on acquisition. This is something that could take the whole presentation. If you wanted, in the book, we dedicate a whole chapter to it, around 50 or 60 pages, just on acquisition. It's obviously very important. If you have someone that does it wrong, it's going to tarnish a lot of the evidence that you want to find. And we also have people that very often walk away with broken images, and it's kind of, you're kind of lost at that point. Take an image, you don't test it before you leave, and you go back to the lab, there's not a whole lot that volatility or any other tool can do for you because you don't have the data there to analyze in the first place. So this is kind of one slide to help you out with this. We have people that want to interact with the system while they're taking memory, or they kick off the memory tool when antivirus is running, when other security tools are running. That's a really good way to screw up the memory dump and to get an invalid one that you're not going to be able to analyze. We also have people who get kind of anxious and they kick off the memory tool. It may take 20, 30 minutes to acquire memory depending on how much RAM there is, and then they start running the live IR tool. So you have these other tools that are examining the system state right when your memory acquisition tool is running, which is not what you want. You really need to train yourself and train the people that you're working with to run the acquisition tool, walk away, and come back when it's done. Because we've had people just give us memory images we couldn't really work with because they violated a lot of these bullet points here. The best way to acquire memory at this point is through software. In the past, you were able to get it through hardware protocols like FireWire was really popular, but it's really hard to use this at this point. A lot of machines don't have FireWire. The other thing is that FireWire by default is limited to 4 gigabytes. So you have a machine with 8, 16, gigs of RAM or more, and you're only going to get the first gigs, which is not going to be very helpful. So the way we do acquisition, and the way most people do it now, is through software. To do this, you need to load some type of third-party program. If you're familiar with the older Windows or Linux, you had device physical memory. On Linux, you had dev-mem, but those aren't there anymore. They're a huge security risk. They've been turned off. So your third-party program needs to load a driver that can then access the physical pages by itself. Some of the advantages to this, using the software method, is that it can be loaded onto any of the support operating systems. So if you think of Windows and you look at a laptop versus a server, the type of hardware there is completely different, and you have completely different memory layouts. But if your tool supports something like, say, Windows 7 or one of the Windows servers, it really doesn't matter what the underlying hardware is, it's still going to be able to acquire memory. The other nice thing with software acquisition is it can be done over the network. So has anyone used, or does anyone use ArchCon in their environment? All right, a few people. So this is one of the ways that we do memory acquisition over the network and memory analysis over the network is through something like ArchCon, where you have that memory exposed over the network that you can then access. Some of the disadvantages to the software way, one of the biggest obstacles is you need administrator access. So if you walk up to a machine and it's locked, if the person's not going to cooperate with you and to give you access to the system, it can be difficult to get memory from it. The other thing, as we'll see a little bit in the slides, is the potential for malware interference. There's tools that specifically look for, there's malware that specifically looks for acquisition tools, and they also look for events in the system that say, hey, memory is about to be acquired, is there something, do you want to act on that before? And so you'll see tools essentially clear themselves out of memory before the memory can be taken. Another source of memory that people use, again, volatility supports a lot of operating systems. We're going to kind of focus on Windows for this one. And one of the sources on Windows is the hibernation file. So every time you hibernate your laptop, essentially what happens is a copy of RAM gets written to hibernfile.sys. Next time you open your laptop, when you wake from the hibernation, all of that gets read back into memory. The interesting thing about this is that it doesn't get cleared. So Windows is going to copy that data from the file back into RAM, and then it's essentially going to leave it there. It's going to change some of the metadata at the beginning of the file, but the contents of RAM will still be intact. So if you're given a laptop to investigate if the person didn't take a memory capture before, you can use the hibernation file as a type of memory acquisition. The other interesting thing here is the volume shadow service. So on Windows Vista and 7 and 8, some of the servers, you have the volume shadow service. And what it does is it makes full copies of the disk as changes are being made. So what's interesting about this is the volume shadow copy will have copies of hibernfile.sys going back in time. So we pulled systems that have 10, 20, 30 volume shadow copies, and essentially what we have is memory dumps going back into the past. We have scripts that you can then run over those, find the unique artifacts from each one, and then you get essentially a timeline that can go back months of what exactly happened on a computer. Two acquisition notes though. Pulling the hibernation file is not a replacement for doing proper acquisition. So when people figured out the usefulness of hibernfile.sys, when Matthew Sweets released his tools that could actually analyze them, you would have people that would just walk up to a machine, hibernate it, bring it back to the lab, take hibernfile.sys and think that they did proper acquisition. One of the big issues with that, though, is when you hibernate, all your network connections get terminated and your DHCP lease is released. So if you look at, say, the active connections on a system before and after hibernation, you'll have all your connections before, and then after hibernation, there's nothing there. We'll see with volatility that you can go back and scan for remnants of those old connections, but that's not really what you want. You want the actual state of the system when you walked up to it. And this is one of the big reasons why you still need to use software tools versus just relying on hibernation. The other thing is that the other thing you realize is that the page file is not a full capture of memory. On our mailing list, on chat, on Twitter, almost, I would say, a couple times a month at this point, we still have people that ask, I have the page file, I run volatility against it, I run these other memory tools against it, and it doesn't work. Like, what's wrong with your tool? A page file is not a capture of RAM. It's just a set of pages that couldn't be placed into memory at a certain time because of memory pressure, were written out to disk, and so they're kind of trapped there. But it's not a complete capture of RAM as if you had the hibernation file, or as if you used something like dump it. So for the rest of the talk, what I want to do is go through some of the common questions that we see in incident response and how you can answer them through memory forensics. And the other thing to realize is that I certainly like disk forensics, I like network forensics, we use them a lot, but there are questions and there are scenarios that you can't solve, and there are questions you can't answer solely through this type of forensics. And we'll see that with memory forensics, though, we can kind of fill those gaps. So one of the first things we get is trying to figure out what processes or what pieces of code we're talking about on the network. So your network team comes back and they say, hey, we saw this machine beaconing out to a particular IP address on a particular port. It was using this protocol. What on the machine was actually responsible for that connection? So one of the first things we do in those investigations is start looking for networking structures. In this case, if you've never seen volatility before, in black is the command invocation. So volatility is a Python script, Python vol.py. -f is the path to the memory dump. Profile is when you tell volatility what type of system you're analyzing. So we see this is Win7, ST1, 64-bit. And then the last argument is the plugin. And in this case, the plugin is NetScan. And what it's going to do is carve through physical memory looking for network connections. And because it's carving, this is not only the active ones, it's also previously terminated ones that haven't been overwritten. So these network connections are represented by a structure. The network connection terminates, and it's not until something else overwrites that data that is going to be gone. So in this case, it's pretty easy. If we had an indicator of a particular IP address, we run NetScan. We look for the foreign address and port that matches our indicator. And as you can see, the network connections have a pointer to which process started them. We now immediately know out of the entire memory dump, out of all the processes that are running, out of all the kernel drivers that are loaded, the particular region of code that's responsible for that connection. Another common question is once you start looking at processes, especially with more modern malware, it's very rare that you'll see a process out on its own. A lot of times what the malware wants to do is inject code into another process. If they inject into Explorer, some of the other long-running processes, until the machine shuts down, that malware is still going to be active. So we want some robust ways of finding injected code and being able to extract it. So there's three types we're going to look at. One is shellcode injection, the second is remote DLL injection, and the third is reflective DLL injection. And again, to realize or be aware of, you can do all of these across the other operating systems. You can do them across Linux, across Mac. We have complementary plugins on those operating systems that detect them the same way. I'm kind of just focusing on Windows because I assume most people would be more familiar with that. So for those not familiar, shellcode is the idea of taking raw instructions, raw machine instructions, injecting them into a process and then having them run. So if you've seen shellcode before for exploits, normally the first payload is going to be some assembly instructions that then download a larger piece of code. So with volatility, you can use the malfind plugin. In this case, we're looking at a memory sample from a machine with Zeus. And what it's doing is it's walking all the memory regions looking for pages that are mapped in a suspicious way. You can see that I have it highlighted here on the second line of output. It tells us that the protection is executable, readable, and writable. That's not a combination that should ever be valid. Your code should be mapped executable and readable, and your data should be mapped readable and writable. There's no real reason on modern systems to have pages with those flags set. One place you'll get some false positives on this is if you run on like a browser that has a JIT JavaScript compiler, or if you run on like your Flash plugin. That's one of the few exceptions where code is actually generated at runtime in a valid context. So you can certainly whitelist those out. But in this case, you can see that the code was injected into Explorer. If you can read assembly a little bit, you get assembly at the bottom. You can see that a number is being moved into a register, and then it's being jumped out to a hard-coded address. So it's a very common way of hooking APIs. The second type of injection we want to find is remote library injection. So what's happening here, when we talk about library on Windows, we're talking about DLL files. In this case, what the malware wants to do is inject a DLL into another process, either to steal its data, to hook some of the code, or for persistence. So very often what we'll see, if there's actually a file on disk, the file on disk is very small, and its sole purpose is to load very quickly, throw a DLL into a process like Explorer, and then the process that does the injection goes away. But that DLL is going to live on because it injected into a long-running process. So with volatility, you can use the DLL list plugin. It's going to list all of the DLLs that are loaded, and at that point, if you're doing it a manual way, you can look at all the DLLs, say, are any of these suspicious, or these ones I'm not familiar with, Or if you script on top of volatility a little bit, you can very easily incorporate a whitelist. So you can take all of the DLLs from your base image, run DLL list against all of the processes, and then look for the DLLs you don't know about. Because malware wants to hide in the ways that DLLs can be found, they're going to essentially manipulate the data structures. So if we go back to DLL list a second, essentially what it's doing is inside the address space of every process, so inside the actual process address space, there's a list of DLLs that are kept by the loader. Every time you call load library, every time an application loads a DLL, that's going to go through the loader, is going to keep track of what DLL is storing, and that's going to be placed in a list. If you've ever used Ali-Debug, if you've used like Process Hacker and you looked at the loaded modules, it's walking the same list that DLL list walks. Obviously though, malware doesn't want to be found in this list. It wants to inject the DLL, and then it doesn't want you to go back and immediately see it and find its full path. So it's going to try to hide itself. So if you look at the loader data structures in Windows, you see that there's actually 3 lists. There's one, if you look at the columns here, the inload, init, and in-memory. The 3 lists, inload is the load order, so when they're actually loaded in the process. Init is when the order they are initialized, and then in-memory is ordered by the address. So if you use some of the tools on a live system, they're going to walk all 3 of these lists for every process. They're going to list the DLLs that were loaded, and that's how it's going to tell you from like a live system perspective which DLLs were inside or processed. So again, if you look at half-decent malware, if you look at the advanced ones, the first thing they do after injecting the DLL is break all of those lists. If you've ever seen how processes break out of the list, it's the same idea. You have a list that you walk, each entry is going to be a DLL, and if you break that list, it's not going to be found. So what we're doing here is running LDR modules. It knows how to find hidden DLLs that break from these lists, and this is a plain sample. So this is called like the cousin of Stuxnet or something like that. It was a pretty advanced sample. It did some interesting techniques, and it was one of the ones that broke from all of the lists. So again, this would be very difficult to find on a live system. From a user land perspective, it would be even more difficult. You might have some better luck in the kernel. But for memory forensics, we have access to data that you don't get on a live system. So what LDR modules does is it looks from a kernel perspective, it finds all of the files that are being mapped into the process, all of the DLL files that are being mapped into a process, and then it compares them to the user land list. So what you see here is inside of services, we have a shell 32 DLL being loaded. It's at a particular address, but the Windows loader doesn't know about it. So again, on a live system, you're kind of out of luck, but with memory forensics, this is going to stand out pretty well, and you now know this is something you need to investigate. And then the last one we'll look at is reflective loading. And this is pretty interesting. This is, again, this was somewhat developed by like the original Metasploit guys. And this is the idea of injecting a DLL without writing anything to disk. If you look kind of at the history of Metasploit and real attackers as well, again, they were exploiting things over the network. They had vulnerabilities that could be reached remotely. But what the stages would do, what the payloads would do at that point is they'd load some shellcode. The shellcode would read a DLL over the network. They would then write that DLL to disk, and then we call load library on it. That's going to leave a lot of artifacts. First off, we have a DLL on disk. If you load a DLL in that way, it's going to show up in DLL list. It's going to be in this loader list, and this is not really what you want to do if you're an attacker. You don't want to leave those artifacts around. So the next kind of stage of that is you still exploit a process, you still have shellcode running. Your payload's still going to read the DLL over the network, but instead of writing it to disk, you're just going to kind of emulate the loader and load that DLL directly. So now you have a DLL in memory, it can do everything normal code can, but there's no artifacts on disk of it, and the loader doesn't know about it either. So really the only way you can find that is to specifically go look for some of those characteristics. So again, we have the malfind plugin that can do this. In this case, you can see it's hitting on a few indicators. So the first one is the protection is still wrong. It's still execute read write. You have a few pieces of malware that we've seen that are smart enough to have the page be executable, readable, and writable. They then fix up the code how they want it, and they go back and change the protection flags. So if you have a skilled enough attacker, they can bypass that check. But what they can't bypass is the other things you see in red, the bad tag, and then also what's being mapped. So what's being mapped is NZ. Does that look familiar to anyone in the hex dump? So that's the beginning of a PE file, so volatility is going to look for that. And then the bad S requires a little bit of Windows knowledge to understand. So when a region gets mapped into a process in memory that's going to be represented by a VAD structure, and then the VAD tag is going to change based on what gets mapped. VAD S essentially stands for not file back, so it's just an anonymous region of memory. If we had a file back region, then we would have a different VAD structure, and we'd have linkage to whatever file was mapping. So what volatility's flagging on in this case is it's saying, I see a VAD S region, that should just be an anonymous region that's being used for data, but I see an MC being mapped there. So this is a very good indicator, even outside of the protection flags, that code has been injected. With volatility, we have the DLL dump plugin that you can then instruct to dump the DLL at this address, you rip it out of memory, and then you can do your reverse engineering and other analysis on it. So even though it doesn't exist on disk, even though there's no way to pull that representation directly, through volatility, you can extract that out of memory and then do your binary analysis on it. And then finally, the last thing to look at in user land is the API hooks. So one of the main reasons for injecting code into a process is to be able to control it. So if malware wants to lie to, say, the process listing tools, to the network connection tools, if they want to steal data that you're entering into your browser or other applications, that can all very easily be done by hooking it. So with volatility and the API hooks plugin, what we do is go through and look exactly for that. We often get asked why this plugin is slow, and it's slow because basically what we have to do is for every process that's in memory, we have to enumerate all of the DLLs that are loaded, we have to find where the application is, and then we have to go find every function that's imported and every function that's exported. If you look at a normal process, that's going to be several thousand per process, and if you look at a normal Windows system, you can have many processes running. What we have to go back and do is look to see, are these functions hooked? With API hooks, you have the --quick parameter. That's going to look just for the DLLs and the functions that we've seen hooked before. But if you want a really thorough look, you want to look at everything. So this can be slow, but it's also very comprehensive. It's we haven't seen any malware in a long time that can hook functions correctly and also bypass this plugin. So it is slow, but it's also worth running. So the next thing we'll look at is some of the kernel rootkits. Everything we talked about so far can be done in user land. So a process, even without admin privileges, without any special privileges on the system, it can hide its DLLs, there can be hooks placed within it. You don't really require any special privileges for that. But there are cases where you want to perform certain tasks that do require kernel access. One of the first things we see with kernel rootkits is the ability to hide processes. So you'll have a piece of malware that has several components. One is the kernel driver that's being loaded, and then you have resources in user land that it wants to hide. It wants to hide processes, it wants to hide files when you open something like Explorer, and we obviously want to be able to find that through memory forensics. So to find hidden processes, we have the PS Crossview plugin, and what this does is it enumerates processes in a number of different ways, essentially to make it very hard for malware to hide from all of them. So what we have here is the offset column is where we find the process, the name, and the PID, and then all of the other columns that have true and false, they're essentially telling you if a process is found in a certain resource. And the thing to realize here is that the PS column, the PS list column, the first one, all you have to do is hide from that one source, and you're never going to be found on a live system. You break yourself out of the process list, and then Task Manager, Sysinternals tools, all those other ones, they're never going to find you. You're not in the active process list anymore. Your process is still going to run, the code's still going to execute, but you're not going to be in that list, and so the live tools won't find it. Even if you have a kernel driver that looks at the list in memory, or calls the process enumeration APIs in the kernel, it's still looking at the same exact list. So again, you're not really going to find this process on a live system, but with memory forensics, you have other ways to find it. So if you look at this one that I have highlighted in red, you can see that it's false in PS list, so it's been broken out of the process list, but we find it 6 other ways. So this is an immediate indicator that there's some type of malware that's hiding the process from the live system, but it obviously doesn't do a very good job of hiding from memory forensics. Another thing we see very often is rootkits using callbacks to control the system. For people in the room who aren't programmers, essentially what a callback lets you do is register for some event, and then when that event happens, your code gets called. So in Windows, there's a large number of callbacks. I listed a couple that we see malware using a lot. So you can register callbacks for when processes are created, when DLLs are being loaded into a process. And essentially what happens is you get control before that event happens. So we've seen very crude malware that hooks the process creation callbacks. If they see antivirus being loaded, if they see security tools being loaded, they just stop it from loading. They essentially say, no, this process can't load, and then it's not going to work. It's kind of a loud way of doing it. Obviously, if I'm trying to load my tool and it doesn't load, I know there's something interfering with it. So it's not very stealthy, but it is effective, especially if you have someone who can't, do deep analysis on the system. You also have a callback for when DLLs get loaded. So we've seen malware that wants to hook every DLL that gets loaded into every process. So what it does is it hooks the thread creation callback right before the DLL is getting loaded. It hooks whatever functions it wants, and then it lets the DLL actually load. So before that DLL, before that process can even use that DLL, it's already hooked and malware already controls it. It's kind of game over at that point. There's also callbacks for every operation in the registry. So if you want to read a key, write a key, enumerate keys under a certain parent key, if you want to look at the values under a key, the rootkits can control all of that data. Also, file system registration. This is something Stuxnet used to infect systems. This is also used by TDL3. And then also the bug check one. So we've seen malware that wants to, a bug check is essentially when you have like a blue screen of death. Depending on how your machine's configured, that's going to take a memory dump of the system and write it out to disk. So there's malware that will look for that happening, and before it actually lets the blue screen happen, it goes and scrubs itself from memory. One of the ways that you can do memory forensics is by essentially blue screening the machine. If you see not my fault from sysinternals, that's essentially what it does. It triggers a bug check to get a memory dump. So this is a callbacks plugin. It's going to find all of the callbacks. It works in two ways. It walks the list that we know about to find callbacks, and it also does carving for them. And in this case, you can see that a weirdly named kernel driver 00482A has the thread notifier routine callback registered. So we know that this is malicious. Volatility tells you the address where that callback is registered. You can then go back and reverse engineer that address to see what the malware is actually doing. The malicious device handlers, this was another tactic of Stuxnet. So essentially what it's doing is registering itself at the bottom of the file system stack. And this is how it was able to infect devices as it was plugged in. It was also if you had, say, a USB stick that was infected with Stuxnet and you plugged it into a system that had Stuxnet running, you wouldn't see Stuxnet's files there. It's able to filter the information that was being read before userland sees it, because it's doing its filtering in the kernel. Has anyone ever had to deal with TDL3 before, any of the variants? Very painful, not fun time. Okay, so TDL3, it had some interesting techniques. One of the things it did was when it hooked the driver IRPs, it didn't hook the indexes directly in the function table, as most malware did at the time. It actually did inline hooks on the specific handlers. So again, with volatility though, if you run driver IRP, you run it with the verbose flag, one of the things it checks is for those hooks. So we were able to detect TDL3 that way, and at the time, there was actually no live tool you could run to find TDL3 when it first came out. It essentially had a catalog of all the ways forensics work and beat all of them. It was a pretty interesting piece of malware. So one of the last things I'm going to talk about is specific infections. So if you saw the keynote, if you were in the room before, what people want to do is have some knowledge of what does something look like, what does a piece of malware look like, what does a tool look like in memory, what does it look like on disk, so you can go scan for that again, or in real time you can monitor for it showing up. So in volatility, we have a couple of the more popular malware samples that we've seen. We have tools that can automatically do this. It can find the malware in memory, and then it can go get the context of the specific infection. So in this case, what we're looking at is the Zeus scan plugin. This is going to walk through memory, find instances of Zeus. It's going to find the keys that are in memory, and then it's going to decrypt the configuration. So it's going to tell you where the files are on disk that are being used, the processes that are associated with it, and it's going to give you the key that can, Zeus use multiple keys, the key that can not only unlock files on disk, but can also decode the network traffic. Another thing we have is the mutant scan plugin. So individual pieces of malware like they'll register mutants to notice when, or to mark when the machine is infected. That mutant is going to persist across processes. So if they, say you have a person that clicks a link and it infects their machine, the malware will place a mutant on the system. If the same person clicks the link A few days later, the malware doesn't want to reinfect it. It could overwrite its own data. It could put the system into an inconsistent state. But with that mutex there, it's like it's marking the system. So the volatility, we can find all of the active mutexes. If you have a database of malware you've seen before, it's very easy to compare against that. And then, as I said before, we also have the YAR support. So with volatility, you can do individual YAR rules on the command line. You can also give it a directory or a set of files with YAR rules built in. And what's nice about this is it doesn't just tell you, yeah, this rule matched, or no, this rule didn't match. It actually gives you the context of where it was found. So it tells you the individual processes where the rule was found. It tells you the address in the processes where the rule was found. Or if it was found in the kernel, it says this rule matched within a particular kernel driver at this address in the kernel. So you get very specific context of what you're searching for. And then the last few slides we'll look at is some user interaction on the system. One of the first questions we get pretty often when we're doing incident response is who actually caused the machine to get infected? Who was responsible for clicking the link, running the malware, who installed some piece of software that was vulnerable? And one of the easiest ways you can do that is through memory forensics. Each process has a set of security identifiers associated with it that map it back essentially to the users of that process and whatever permissions it has. So in this case, we're grepping for, we're running the get_sys plugin, we're grepping for explorer.exe, and this is going to be unique for every user that's logged in. In this case, you can see the first one, it tells us that Larry owns that Explorer, and the second one is for the user Justin. So now what you can do is figure out what processes belong to that session. Now you know which user it maps to, and now you know the person that got the machine infected. A follow-up question to that we often get is what type of access did the attackers gain? They compromised the system, but what did it actually net them? What type of provisions did they have? So this was actually from the screenshot is from one of the ArchCon challenges. Jack Kirk from GE does some very real-world, lifelike forensic challenges, and this is one of the ones that we analyzed and did a blog post on. So we're trying to answer this question: what type of access did the attacker gain? If you run get_sys, if you look at the first one, we're running on logon. You can see that it's local system administrators, everyone, authenticated users. That's pretty common. We then run it on LSAS. You see the same 4 permissions. Pretty common. On the other hand, though, when we were doing the analysis, we saw that explorer.exe had code injected into it. So we run get_sys on that one, and you can see at the bottom in red that explorer.exe is running as enterprise admin, domain admin, group policy creator. This is a really good indication of what the attacker got. You now know that the person had full domain access to the network. You can figure out what user account got that compromised. And this is actually a really good remnant of a pass-the-hash attack. This is exactly how it's going to manifest in memory. And then the last thing we'll talk about is the ability to recover attacker input and output. So one of the things that during the last talk that was spoke about was attackers like to use command.exe. They like to use the WAR from the command line to package files and then send it out on the network. And it's actually a pain if you don't have memory forensics. You can have, if you have network forensics, even if you have full PCAP being full packet capture, essentially what you have at that point is an encrypted WAR file. You can tell your client that, yeah, data was stolen, but you don't know how much was stolen, you don't know exactly what was stolen. But if you can go back to memory and get the password for that file, you can then open the container and give your client much more context. So there's been plenty of cases where we've been able to do this. The console's plugin in volatility has the ability to not only determine what was typed into command.exe or PowerShell, but it's also able to get the output. So it's basically like you were looking over the attacker's shoulder as they were on your system. So many times we get a memory dump over in consoles, and you see exactly what the attacker typed in. You then have the password to the RAR file, you have the password to like backdoor accounts that they've created, and even if they aren't doing those activities, you still know everything that happened in your system. You can very easily automate your incident response, depending on how the attacker got on the system and interacted with it. The other thing to realize is that this information is not kept in command.exe itself, it's kept in the host process. So even if you have an attacker on the machine, they use command.exe, they close the terminal, you come back and take your memory capture a week later, that information can still be stored. If it's not in command.exe, it's going to be in the host part of that process. So that's the end of my talk. In conclusion, if you're not doing memory forensics, you should be. If you're not doing memory forensics, you're going to miss information that could be vital to your investigation. If you don't have memory, you can there's going to be malware and attacker techniques that you'll just never find because they only manifest in memory and the tools only work there. So that's the end of my presentation. Are there any questions on this? Yes.
Hey, Andrew, great presentation. How do you apply these techniques to embedded devices, like the fastest-growing segment, like the Samsung TV in my living room runs Linux? So if that gets popped, what are the options?
So the biggest issue is actually getting memory dump off the device. So we have had where if you have some sort of like physical, like not a physical access like in your hand, but like you get a console on the machine, if you turn like SSH, and then you can root the device, then you can pull memory off. And that's one of the biggest issues right now, especially on the Android side, is having to get rooted if you're going to do it from a software perspective. But we've had like, it's not just phones, but like random Android devices where we were able to get on there. Android is not that secure by default, so there's many ways you can root the devices. And then there's an open source tool called Lime. It's Lime friendly, it's on Google code. It's a kernel module that can pull memory off Linux systems. And then once you get that memory dump, you can then directly use it with Bullet. So we've actually done quite a few like interesting Android applications, but we've had some where we knew it was compromised and couldn't do it because we can't get the memory dump. So that's kind of the only barrier, which is a huge barrier. Any other questions? All right, thank you for attending my presentation. Feel free to contact me.
There's been a slight change to the schedule. That the keynote is going to be held in here in about 5 minutes, so if you want to take a health break, now's the time to do it. Versus here. There you go. The sessions that we're going to be at this time have been moved until after lunch.
Question.
Yes, sir.
Do you guys have any extra batteries? My mouse clicker is dead. AAA.
Mine. I'll go find out.
Thank you. I
That's why I'm
appreciate it. I thought you'd be the right person to reach out to.
I'm the right person. All right.